Good day, students. The second lesson in Module 5 is about Lewis structures. What are Lewis structures? These are electron dot structures. Okay, here the dots represent valence electrons of atoms. A stable molecule results when a noble gas configuration is achieved for all the atoms. Noble gas configuration or noble gases have 8 valence electrons. So there are 8 dots supposedly in noble gas electron dot structures. So since we have 8 here, we have the so-called octet for the 8 dots. So main group elements tend to or want to achieve a noble gas configuration. So for example, we have carbon. Carbon will want to have 8 electrons in total, valence electrons, just like noble gases. Hydrogen, on the other hand, wants to have 2 electrons in total, or duet. Calculus structures are line bond structures. So if Lewis structures are electron dot structures, calculus structures are the line bond. Here, a 2 electron covalent bond is indicated as a line drawn between atoms. So here, for example, in methane, we have our line here. So in this one bond, one covalent bond, there are 2 electrons sharing that bond or shared in that bond. So here we have our methane electron dot structures. For example, we have our carbon. Carbon has 4 valence electrons. So we have our 4 dots here. 1, 2, 3, 4. Hydrogen has 1 valence electrons. So there is 1 dot only for hydrogen. For this hydrogen, we have 1 dot. For this, we have this one. And for this hydrogen, we have this dot. Okay, so for these electrons here, we have the 2 electrons shared between carbon, one from carbon and one from hydrogen. So these 2 electrons here become a line, or connect to form a line in our calculus structures. These 2 electrons, on the other hand, is formed, or a line is drawn between these 2 electrons to form this line here in the calculus structures. And for this, we have here our line, and for this pair of electrons, we have our single line here. Okay, so a 2 electron covalent bond is indicated as a line drawn between atoms. For lone pairs, for electrons not involved or not shared between the atoms, it's like this one, they stay as is in the calculus structures. Okay, so as is in the calculus structures. We have another pair of electrons here which are not involved in bonding, so they stay as is in the calculus structures. Now, the number of covalent bonds an atom form depends on how many additional valence electrons it needs to reach a noble gas configuration. Like for example, hydrogen. Hydrogen is in group 1, so it has 1 valence electron. Again, for hydrogen, its maximum number of electrons is 2 in a bond, or in a structure when it is bonded to other atom. So therefore, since hydrogen needs 1 additional valence electron to form a duet, it will have 1 bond. So the number of covalent bonds an atom form depends on how many additional valence electron it needs. Since hydrogen needs 2 electrons only, so since it has 1 valence electron already, it will need 1 more for it to have 2 electrons. Therefore, hydrogen will form 1 bond. Okay. Carbon, on the other hand, has 4 valence electrons. So 4 valence electrons for carbon. So to reach a noble gas configuration has 8 valence electrons. Noble gases have 8 valence electrons. Since carbon has 4 valence electrons, it will need 4 more to reach an octet. or to have 8 valence electrons in total. That is why carbon will form 4 bonds. So 1, 2, 3, 4. Nitrogen has 5 valence electron. So to reach noble gas configuration or to have octet, it will need 3 additional electrons. That is why nitrogen will form 3 bonds. 1, 2, 3. Oxygen is in group 6, so it will need 2 additional valence electron to reach a noble gas configuration. Therefore, oxygen will form 2 bonds. Okay, 1, 2. Halogens have 7 valence electron. So to reach noble gas configuration, they need 1 additional valence electron. Therefore, halogens form 1 bond. Now, the electrons which are not involved in bonding, just like in ammonia here, they are called lone pair or non-bonding electrons. Now, how do we write Lewis structures? First step is we draw the skeletal structure of a compound, showing what atoms are bonded to each other. Here we put the least electronegative element. So we will compare the elements present in a certain compound, and then the element which has the lesser electronegativity or least electronegativity value will be put in the center. Then we count the total number of valence electrons. If there is a negative charge, we will add 1 for each negative charge, and if there is positive charge, we will subtract 1 for each positive charge. Then we complete octet for all atoms except for hydrogen. No? For hydrogen, 2 electrons na siya total. If structure contains too many electrons, we form double and triple bonds on central atom as needed. So we will follow these steps in writing our Lewis structures. Let's have first an example. Write the Lewis structure of nitrogen trifluoride. Between nitrogen and fluorine, nitrogen is less electronegative, so it will be put in the center. Okay, so this is our skeletal structure with N in the middle, since it is the less electronegative atom. Next step is we count the valence electrons. Nitrogen is in group 15, so its valence electron is 5. Fluorine is in group 17, so its valence electron is 7. Okay, so to count the total valence electron, we have 5. This is from nitrogen. Since there is only 1 nitrogen atom, so 5 times 1, we have 5. For fluorine, its valence electron is 7. Since there are 3 fluorine atoms, so we will multiply 7 by 3. We get 21. 21 plus 5, we have 26 valence electron for nitrogen trifluoride. Next step is we draw single bonds between nitrogen and fluorine atoms and complete octets on nitrogen and fluorine atoms. So first we draw a single bond. Okay. So after drawing single bond, we now complete octet on nitrogen and fluorine. So this is our nitrogen atom, and these are the electrons surrounding nitrogen. So around nitrogen, we have 3 single bonds. 1, 2, 3. Each of these bonds, again, has 2 electrons. So there are 2 electrons in a bond, in a single bond. Therefore, as of the moment, nitrogen has 6 electrons in total. 1, 2, 3, 4, 5, 6. So to complete the octet on the nitrogen atom, we will add 2 electrons or 1 lone pair, so that the total number of electrons around nitrogen atom is 8. No? So you have 1, 2, 3, 4, 5, 6, 7, 8. How about for the fluorine atom? How do we complete the octet in fluorine atom? Let's look at this fluorine atom first. This fluorine atom has one single bond, or one covalent bond with nitrogen. Again, in a covalent bond, a single covalent bond, we have 2 electrons. So as of the moment, fluorine has 2 electrons. To complete its octet, we will add 6, not 2 plus 6 is 8. So we will add 6 additional electrons, or 3 lone pairs. We have first lone pair, second lone pair, and third lone pair. Again, these electrons are called lone pair because they are not involved in bonding. So they are not found in this covalent bond, for example. So now we have how many electrons around fluorine atom? We have 1, 2, 3, 4, 5, 6, 7, 8. So now we have complete octet for this fluorine atom. For this fluorine atom, same with this one, we have single covalent bond. So we have 2 electrons as of the moment. Therefore, we will add 6 electrons, or 3 lone pairs, to complete the octet. For this fluorine atom, it's the same, no? We have 1 single bond, so we have 2 electrons as of the moment. Then we have to add 3 lone pairs, or 6 electrons, to complete the octet. Okay, so that is now our structure after drawing single bonds and completing the octets on nitrogen and fluorine atoms. Okay, here we have the valence electron of nitrogen, 1, 2, 3, 4, 5. Then we have for fluorine, the valence electron. Okay, next is we check if the number of electrons in this structure is equal to the computed number of valence electrons. So in this structure, we have 3 single bonds. So we have 3 single bonds, and each of these bonds again has 2 electrons. So 3 single bonds times 2 electrons each, we have 6 electrons in total. Then in this structure, we have 10 lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 lone pairs, and each of the pair, of course it's a pair, so we have 2 electrons each. 10 times 2 is 20. So 6 plus 20, we have 26 valence electrons. So there are 26 valence electrons here, which is equal to the computed or counted valence electrons. So therefore, this structure now is correct because they have the number of electrons in the structure is equal to the computed valence electron. Another example, write the Lewis structure of the carbonate ion. So first step again is to determine the less electronegative element in the compound. In this case, it is carbon. You can look for electronegativity values in your periodic table. Again, carbon is less electronegative than oxygen, so we put carbon in the center. Next step is we count the valence electrons. For carbon, since its group number, since it is in group 14, its valence electron is 4. For oxygen, it's in group 16, so it has 6 valence electrons. Then in our carbonate ion, it's an ion, so it has charge. In this case, its charge is 2 negative. According to the rule, for each negative charge, we will add 1. Since we have 2 negative or negative 2 charge, therefore we will add 2 electrons. No? So in total, we have 4. This 4 is from the valence electron of carbon. The valence electron of oxygen is 6. Since we have 3 oxygen atoms, we will multiply 6 by 3. And this 2 here is from the 2 negative charge of carbonate ion. So this is 4 plus 3 times 6 is 18. So 4 plus 18 plus 2, we have 24 valence electron. After counting the valence electron, next we draw single bonds between carbon and oxygen atoms. Then, after drawing single bonds, we complete octet on carbon and oxygen. So, to complete octet on carbon, this is our carbon here with 3 single bonds. So, each of these bond has 2 electrons. So, 2, 4, 6. Therefore, to complete the octet on carbon, we will add only 1 lone pair or 2 electrons. So, para ma-8 ang total of electrons on carbon. So, we have 2, 4, 6, 8. For oxygen, this is our oxygen here. We have 2 electrons as of the moment because it has a single bond with carbon. So, to complete its octet, we will add 6 electrons or 3 lone pairs. For this oxygen atom, it's the same. It has a single bond, so it has 2 electrons at the moment. It needs 6 additional electrons or 3 lone pairs to complete its octet. And for this oxygen atom to complete its octet, same, we need to add 3 lone pairs. Okay. So after completing the octet on carbon and oxygen atoms, the next step is to check whether the number of electrons in this structure is the same or equal to the number of valence electron. Okay, so let's count. In the structure, we have 3 single bonds, 1, 2, and 3. So we have 3 single bonds, and each of the bond has 2 electrons. See, 3 single bonds and 2 electrons for each bond, so we have 6. Then we have 10 lone pairs, so 10 lone pairs, and each pair has, of course, 2 electrons. So 10 times 2 is 20. Therefore, the total number of electrons in the structure is 26. However, the computed valence electron is only 24, meaning there are too many electrons in the structure. So what we do here is we form a double bond. So we form a double bond. How do we form the double bond? We can form the double bond between this carbon atom and this oxygen, or this carbon and this oxygen, or the carbon and this oxygen atom. So we could form either of these 3 bonds. So for example, we will form the double bond between this carbon atom and this oxygen atom. What we do is we remove a lone pair from each. We remove a lone pair of this and a lone pair of this, and then we form our double bond. We can also do the same. So instead of putting the double bond there, we will try to do it in the other bond. So we could also form double bond between this oxygen atom and this carbon atom. So saying we remove this lone pair and this lone pair, and then we form double bond. Or could be with the third oxygen atom. So we remove this lone pair and this lone pair, for example, then we form our double bond. Okay, so let's Okay, for example, we form our double bond between this carbon and oxygen atom. Again, we remove lone pairs of each, and then we form our double bond. Now, after forming the double bond, we count again the number of electrons if it is now 24. So let's count. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now we have 24 electrons in our structure, which is the same as with our counted valence electrons. That is why this structure now is correct. Okay, so we have our total of 24 valence electrons. For formaldehyde, there are two possible skeletal structures. First, we have this and this, where is it now? Second structure. Okay. Now we have the so-called formal charge. An atom's formal charge is the difference between the number of valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. The formula for formal charge is equal to the total number of valence electrons in the free atom minus the total number of non-bonding electrons minus the 1/2 of total number of bonding electrons. Take note that the sum of the formal charges of the atoms in a molecule or ion must equal the charge on the molecule or ion. Like for example, we compute the formal charge of this hydrogen, this carbon, the oxygen, and this hydrogen atom. After computing the formal charges of each, we get the sum of their formal charges, and the sum must equal to the charge on the molecule or ion. So for example, this structure is neutral. When we add the formal charges of each of these elements here, you should get a total of 0. Okay? That is what is meant by the sum of the formal charges of the atoms must equal the charge on the molecule or ion. So in the first structure, we'll look at this first structure. So for carbon, its valence electron is 4 again. For oxygen, the valence electron is 6. For hydrogen, its valence electron is 1. Since there are 2 hydrogens here, so we have 2 times 1, our computed total valence electron for this structure is 12. Now, how many electrons are there in this structure? So we have 2 single bonds, 1, 2. Each single bond has 2 electrons, so 2 times 2, we have 4 electrons for the single bonds. We have 1 double bond, we have 4 electrons for that, and we have 2 lone pairs, so we have total of 4. So 4 plus 4 plus 4, we have 8. Therefore, this structure is correct because the number of electrons in the structure is equal to the computed valence electron. Now let's compute for the formal charge of each of the atoms in this structure. Let's start with carbon. The formal charge on carbon is, so in the formula, we start with the total number of valence electrons in the free atom. We know that the valence electron of carbon is 4, so we have 4 minus the total number of non-bonding electrons. So in carbon, this is our carbon atom and the electrons which surround the atom. Non-bonding electrons are the dots that we see, or the lone pair. So in carbon, we have 2. Okay, for the number of bonding electrons. Bonding electrons are those electrons in a bond. So since carbon has 3 bonds here, so carbon has 3 bonds, and each of these bond has 2 electrons. So the total number of bonding electrons therefore is 1, 2, 3, 4, 5, 6. So this is 1/2 of 6. Okay, so 4 minus 2 is 2. 1/2 of 6 is 3. So 4 minus 2 minus 3 is equal to -1. Therefore, the formal charge on carbon in this structure is -1. Okay, let's compute the formal charge on oxygen atom. So the valence electron of oxygen is 6. And then the total number of non-bonding electrons. We will look at oxygen in this structure. The total number of non-bonding electrons, again, non-bonding electrons are those dots that you can see. They are the lone pairs. No? So for oxygen, we have 2. And for the total number of bonding electrons, so we have 3 single bonds. So the total number of bonding electrons, therefore, is 6, since each bond has 2 electrons. Therefore, its formal charge is 6 minus 2 minus 1/2 of 6. We have +1. So the formal charge of oxygen in this structure is +1. How about for hydrogen? What is the formal charge of hydrogen in this structure? So valence electron of hydrogen is 1. The total number of non-bonding electrons. Do we see any non-bonding electrons? We don't have. We don't see any dots. So this is 0. Then 1/2 of total number of bonding electrons. So since we have 1 bond, so we have 2 electrons. 1/2 of 2. So 1 minus 0 minus 1 is 0. Therefore, in this hydrogen, we have 0, or it has no formal charge. Same with the other hydrogen atom. Now, when we add the formal charges of these elements in this structure, we have 0 plus -1 plus 1 plus 0. The total is 0, which is actually the same as with the total charge of the molecule, no? Or it doesn't have any charge, man. So when we add the formal charges, it should also be equal to 0. For the second structure, again, we count first the valence electrons. Carbon has 4, oxygen has 6 valence electrons, hydrogen atom has 1, and since we have 2 hydrogens, we have 2 times 1, the total valence electron is 12. Now, we count the electrons in this structure if it's equal to 12. We still have 2 single bonds, and each bond has 2 electrons, of course. So we have a total of 4 electrons. For the double bond, we have 4 electrons, and for the lone pairs, we have 1, 2, 3, 4. We have 2 lone pairs and 2 electrons each, so we have 4 total electrons. So in this structure, we have a total of 12, which is equal to the computed valence electrons. So this structure is also correct, no? Now, let's compute for the formal charges of the atoms in the structure. For the formal charge on carbon, we start with the valence electron of carbon, which is 4, minus the total number of non-bonding electrons for carbon. Do we have non-bonding electrons? Can you see any dots? We don't have any dots, so therefore, that's 0. For the total number of bonding electrons, so we have 1, 2, 3, 4, 4 bonds. So that's 1/2 of 8. 1/2 of 8 is 4. So 4 minus 4, we have 0. For oxygen, we have 6 valence electron minus. For oxygen, we have 2 lone pairs or 4 non-bonding electrons. Then, for the bonding electrons, we have this 4. No? So 1/2 of 4 is 2. 6 minus 4 minus 2 is 0. So therefore, the oxygen has no thermal charge in this structure. For hydrogen, it's still 0, and for the 2 hydrogen atoms, thermal charges are 0. If you can see one bond for hydrogen, automatic, that's 0 thermal charge. Okay, thermal charge and Lewis structure. For neutral molecules, a Lewis structure in which there are no thermal charges. So that means 0 ang thermal charge of each element. It's preferable to one in which thermal charges are present. Second, Lewis structures with large thermal charges are less plausible than those with small thermal charges. And among Lewis structures having similar distributions of thermal charges, the most plausible structure is the one in which the negative thermal charge are placed on the more electronegative atoms, because the more electronegative atoms tend to attract more the electrons towards itself. So it's possible that it will have the negative thermal charge. It's plausible, no, to have the negative thermal charge on the more electronegative atom. Now, looking back at the 2 structures for formaldehyde, we have this one and the second one. Based on the rules, for neutral molecules, since formaldehyde is neutral, a Lewis structure in which there are no thermal charges is preferable. As you can see, in the first structure, we have our negative 1 for carbon and positive 1 for oxygen. Whereas in the second structure, we have 0 thermal charges or no thermal charges for both carbon and oxygen. Therefore, based on the ruling, the most likely structure for formaldehyde is the second structure. Again, because there are no thermal charges in this structure. Okay, then we have resonance structure. When I say resonance structure, it is one of 2 or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis structure. So, for example, we have benzene. If you have observed, our double bonds are here. Double bond, single, double, single, double, single. And the other structure, resonance structure, instead of double bond here, we have single bond. And instead of double bond, we have our single bond, we have our double bond. So the alternate double bonds are now moved, no, from this carbon to this, like this one. Now this happens for benzene, for example. If, for example, the carbon, the double bond should only be put in these 2 carbon atoms here or this one, experimental results would have revealed that there are 2 different bond lengths. So one for the carbon-carbon single bond and one for the carbon-carbon double bond. However, based on experiment, the results show that there is only 1 bond length for all the carbon-carbon atoms here. So that means to say that the double bond could have been put in this, between these 2 carbon atoms and these carbon atoms and this one, or it could be on the alternate, no, in these 2 carbon atoms here and this one. For acetate ion, we have 2 resonance structures. We have our carbon double bond here and carbon single bond, or the other way around, we have our carbon single bonded to oxygen and our carbon double bonded to oxygen. Again, these structures, 1 or 2 Lewis structures for single molecules that cannot be represented accurately by only one. So either of these, no, could be the structure. So for acetate ion, here we have red curved arrow. This indicates that a lone pair of electron moves from the top of oxygen, so from lone pair to become part of the carbon double bond. So when this electron moves to this bond, we have our double bond formed here. And so that carbon will have octet, no? 1 bond here should be what? Should move to form or to become a lone pair in this oxygen. Because what happens if this bond here, the electrons here, stay as is? Carbon would have 10 electrons in total, okay? Which is, does not follow the octet anymore. So for oxygen, to have octet still, so we have 2, 4, 6, 8, the electron here should move to become a lone pair in the oxygen atom. Okay, so those are the two resonance structures for acetate ion. Then for benzene, so we have the double bond, no? The electrons here move to form a double bond here, and this one here move to this, and this pair of electrons here, the double bond move to form a double bond here to form this structure. Okay, example, draw the three resonance structures of carbonate ion. Remember, we have drawn the Lewis structure for carbonate ion, and I've said the double bond could be put between this carbon and oxygen atom, or it could be what? Here at the bottom, or in the left oxygen, or on the right. No? So what happens here is that from this structure, first, second, and third structure, from the first structure, the double bond is formed when this lone pair, for example, is formed here, or forms a double bond, and the electrons here in the double bond goes to become a lone pair in this oxygen atom. So this structure results. Now, from this second structure to the third structure, this happens when lone pair, for example, in this oxygen atom, moves to become a double bond here, and one of the double bond here moves to become a lone pair in oxygen atom. Okay, so these are the three resonance structures for carbonate ion. Now we have exceptions to the octet rule. We have the incomplete octet, meaning we have less than 8 electrons, just like in hydrogen, in beryllium. Beryllium hydride, we have 4 electrons only in total. Okay, in complete octet, again, less than 8 electrons. So we only have 4 electrons. We also have in boron trifluoride, the total electrons for boron here is only 6. For beryllium, it's only 4. So they do not follow the octet. No? Their electrons in total sa structure are less than 8. We also have odd electron molecules. Just like in this structure here, nitrogen has 5 valence electrons, whereas oxygen has 6. So the total electrons would be 11, which is an odd number. And we also have the expanded octet. So this happens for those atoms with principal quantum number greater than 2, or starting from the third period. They can have more than 8 electrons surrounding them, just like in sulfur, for example. Sulfur is in group 3. So as you can see here, sulfur has total of 2, 4, 6, 8, 10, 12 electrons surrounding it. And it's okay because it is in the third period already. So those elements na nasa second period, they are the ones which follow the octet rule.